Hello and welcome to my data center technical series. This is volume 3.9. This is a bit arbitrary. I just don't want to move on to volume 4 until you understand the basic fundamentals and principles and methodologies in regards to DC resistance and battery testing versus AC conductance and AC impedance. So let's get started really quick. The AC impedance testing methodology is actually the resistance of the cell to the flow of AC current as presented by the resistance R and the inductive and capacitive reactance XL and XC of the internal components. Now this is entirely frequency dependent and the results will vary, again, as I spoke previously about the material science of the batteries, depending on the frequency of the testing device, the amp hour of the battery, 1.5 farads per 100 amp hours, and the charger ripple voltage and current, harmonic currents on the DC bus. Now the absolute value of AC impedance of the cell can be determined by forcing a specified AC current through the battery, and then we're going to measure that AC voltage drop directly on the terminals on the anode and cathode. Z will be the E divided by I. Now admittance is the reciprocal of the impedance, 1 divided by C, and conductance is the reciprocal of the real part of the resistive portion of impedance, 1 divided by R. Now the conductance test applies a specified AC voltage signal that is capacitively coupled to the battery, and the resulting AC current is measured, calculated as 1 divided by E divided by I, or simply C equals I divided by E. Now you can see, I want to go over this very quickly on some of the formulas for inductive reactance, 2 pi times the frequency of the device times inductance in ohms, and then capacitive reactance will be 1/2 pi times F of C, where F is the frequency of the testing device and C is the capacitance of the battery in farads, right? So let's take a look at above me here on these two things at the top. You're going to see the battery equivalent circuit. On this side over here you'll see DC resistance, and on this side you'll see AC resistance. So what this is doing is breaking down the resistance within the battery material and internal components. So you'll see terminal resistance intercells at 12%, the straps and posts, intertiers at 25%, and then the plates of the battery internal, you have 6 2-volt cells in a 12-volt monoblock. Those plates between the AGMs, that's 40% of the battery resistance in total. Then you have the separators, the electrolyte, the inductance, and again some intercell connections there for the DC. Okay, so when you're strictly using DC, a purely resistive load, it bypasses and ignores the capacitive reactance of the battery. This is a huge deal, and it's significant because on larger battery systems, this is essentially ignoring all of that, which can, I would say, drastically interfere in the resolution of the device, and we'll get into that a little bit as we get into harmonics and more later as we talk about 6 and 12 pulse rectifiers and inverters and instantaneous gate bipolar transistors versus silicon controlled rectifiers. So on the other side, on this side up top, you'll see the AC testing methodology, and this is very important. What you want to see there is look at that. So the AC signal is going in parallel to that DC resistance. So because of this, depending on the frequency, again, if it's a bigger battery, if it's a 1950 amp hour vented lead acid wet cell, and this is ignoring DC resistance entirely, but just the noise and the capacitive reactance, you won't see that 40% increase until the battery is open. I've been testing millions of batteries around the world, and this is absolutely true. That doesn't matter what you do at all. So, and then we talk about noise. So you can just see these two basic fundamental principles, again, based on the frequency of the testing device and the amp hour of the battery determines the resolution if you're using an AC-based signal. But I always ask everybody, if you're using a battery that supplies DC current, why are you testing it with an AC signal source? It makes absolutely no sense at all. Right? The DC current's going to feed the inverter, and that's going to be supplied to the load. The DC, the battery is not supplying an AC current to the inverter at all. So it doesn't make a whole lot of sense to me. But I do come back to spectroscopy, and I still believe that running up to 30 different frequencies and calculating different resistances based on the material science of the battery could provide much more information than just simply doing a DC load bank test. But we'll get into more of that later. But let's also talk about the noise here real quick. So hopefully you guys understand those basic fundamental principles. It's very simple, again, using those formulas, but it's up to you. It's up to your organization what you choose. Again, a lot of this is based on cost. So you see a lot of monitoring out there that is implementing AC impedance, AC conductance, because it's very, very low cost to develop and implement out in the field. DC current is expensive, the load banks are expensive, and it's difficult to integrate that. There's a lot of patents out there that people hold that you can't integrate and design appropriately. So let's talk about noise really quick. So what you see right above me is an actual noisy DC bus signal on a 750 kVA UPS, 3-phase power. There's an 11 amp AC signal harmonic riding on the DC bus. So let's come back to impedance again, right, which is injecting an AC current essentially through the battery system. If it's using a 1 amp signal on the battery bus, how in God's green earth is it going to differentiate that signal from the noise floor? The answer is very clear: it cannot. So they don't know that when they implement that out in the field, right? And this is what I come back to the analog to digital converter resolution, the total number of bits. That is, it's directly applicable to this as well. So monitors might work perfectly in a factory where there's no noise. Everything is essentially designed to operate at 100% efficiency. But when it gets out into the field, you have all of these other components that can drastically impact and affect the battery monitoring system. Okay, so again, coming back to this noise, AC impedance in this kind of environment does not work at all. And this is entirely dependent, again, over here. So what you see on this side, and I will be releasing a comprehensive video on IGBTs versus SCRs and switching mechanisms. It'll be, probably 20 to 30 minutes long, maybe even longer. There's a lot of information there and a lot of, electrical engineering principles that I have to walk you guys through so you understand this. But just look at this right here. So you'll see on this side, depending on if you have a 6-pulse rectifier or a 12-pulse rectifier, or if it's an SCR or IGBT, we know IGBTs can turn off and on instantly, but SCRs actually take some time, right? And we'll go over that a little bit later, but because of that, you get more noise with SCRs and DC buses than IGBTs, and specifically IGBTs have different generations. They can switch at different kHz, 14 kHz to 60 kHz. So you'll see different representations all the way on the other side of actually how that signal level and the typical waveform that you see in a 3-phase output, how that actually looks on 6-pulse rectifiers or 12-pulse rectifiers. But the reason this is important, let's just choose a 12-pulse rectifier. The noise on those systems is generally, for the harmonics, is how you calculate this out, is 11th and 13th. So those are the fundamental frequencies times 60 hertz, right? So if you have a 6-pulse rectifier, you would have harmonics on the 5th and 7th harmonic, right? So you'd have around 300 hertz. So this is important to understand, because when you're designing the monitoring system and they're using various frequencies to apply across there, if those frequencies are fundamental components of 60 hertz, it's not going to work at all, because especially if you have noisy DC bus systems, it's going to completely evaporate in the noise floor, right? It'll be gone. And I review these things in detail because in the data center industry, these terms get interchanged and exchanged commonly, daily. Every time I go to a site, someone is projecting to me that impedance and conductance is the same as resistance, because on their terminology, on their marketing material, I call it fluff, on their marketing fluff, they put resistance values because they want to trick you. They want you to think that resistance resolution, which is usually AC conductance or impedance, is the same as a DC resistance methodology, where that's 6 millionths of an ohm, 6 decimal places back on the resolution. These systems do not have that kind of resolution, not at all. So thank you so much for tuning into this. I hope this makes a little bit more sense, again, as an additional primer onto the testing methodology videos that I've created previously, and because some of this stuff is difficult to convey, and that's why I love creating these videos for you all out there. Thank you so much. Have a wonderful day.